In this lecture, we'll start studying the algebra of species. This various algebraic operations that you can perform on species, which are then reflected in their generating series. So the first algebraic operation, and perhaps the simplest, is that of the sum of species. So here's the definition. If f and g are species of structures, then f plus g is the species defined by f plus g applied to the set U is f of u disjoint union g of u. So in this lecture and the following lectures, I'll be using this plus to denote disjoint union. Sometimes it could be that f of u and g of u, there are structures in common between f and g, and so when you take f of u plus g of u, you need to make another copy of these common structures. Another way of thinking about this is if you have two sets, then x plus y is defined to be the set x cross 1 union y cross 2. In this way, you're sure that these elements are different from these elements. But so that's what disjoint union means. And now I need to define what the transport of structure is, and so I define it in the most obvious way. F plus g applied to sigma of s is going to be, so now if s is in f plus g, so you say sigma is a bijection from u to v, then s is in f plus g of u, which means that s is either in fu, so then this will be f sigma of s if s belongs to f of u, and this will be g sigma s if s belongs to g of u. That's the transport of structure. It's more or less what you would expect. And visually we can write this definition as follows. An f plus g structure, well, abstractly we would denote it by this kind of a picture. An f plus g structure is either an f structure or a g structure on the set. So what I'll do is I'll write it as this is equal to either an f structure on this set or a g structure on this set. That's the visual description of the sum. So in other words, an f plus g structure on a set U is either an f structure on the set U or a g structure on the set U. Let's look at some simple examples. So recall that we have the 0 species. 0 of U is the empty set for all U. And if we take f any species, then f plus 0 of u is equal to f of u disjoint union 0 of u, which is f of u disjoint union empty set, which is the same as f of u. So the species f plus 0 is isomorphic to the species f, or in other words, we say that they're the same species. So we'll write f plus 0 is equal to f. Let's look at another example where there may be a duplication of structure. So let's say, what is x plus x of u? So recall that x of u is just singleton u if cardinality of u is 1 and it is empty otherwise. And so x plus x of u is going to be xu plus xu. What we should think of this disjoint union as xu cross 1 plus xu cross 2, which we can think of as xu cross 1 comma 2. So this is equal to this set singleton u times the set 1 comma 2 if cardinality of u is 1 and empty set otherwise. Let's look at just one more example in the same vein. What is 1 plus x u? Well, you can easily see that this is going to be singleton u if cardinality of u is 0 or 1. Recall that 1 of u is given by singleton u if cardinality of u is 1 and empty set otherwise. So this is going to be either the set is empty or the set has cardinality 1, then you will get the singleton u, and otherwise you will get empty. Okay, so those are some very simple examples of sums. We look at more interesting examples later on. Before that, let me explain what happens with generating series. So that's an easy theorem that the generating cycle index generating series of f plus g, so that's a polynomial in infinitely many variables, is zf x1 x2 plus zg x1 x2, and this implies that we also have f plus g. The generating series for the species f plus g is the sum of the generating series, and the type generating series is the sum of the type generating series. These two follow from the first statement because we can derive the generating series and the type generating series from the cycle index series by substituting different values into the variables x1, x2, x3 and so on. So let's look at a nice example of that. So let's define the species of odd cardinality sets, E odd u. We'll define it to be singleton u if the cardinality of u is odd, and we'll define it to be empty otherwise. And similarly, let's define E even u to be the cardinality of u, singleton u if the cardinality of u is even and empty otherwise. Then it's easy to see that E, the species of sets, is E even plus E odd, and the generating series here is E of x. Well, that's going to be E even x plus E odd of x. And if you just think about what these are, the identity of formal power series that you get is that xx, that's the generating series of Ex, we saw that in one of the earlier lectures, is hyperbolic cosine x plus hyperbolic sine x. Now let's extend the notion of sum from two species to several species. So we'll say that a family Fi indexed by some indexing set I is said to be summable if for every finite set U the collection I in I such that FIU is non-empty is finite. So now if this is the case, then we can define the species Fi summation I in I Fi. This species is defined by, so I should say define the species. This should be summation I in I Fi U, where by this I mean the disjoint union of the family of sets FIU. Another way of thinking about this is that this is the union over all I in I FIU cross singleton I. Now note that because of the hypothesis here, this is going to be a finite disjoint union, and so this is going to be a finite set. Disjoint union of a finite disjoint union of finite sets is of course finite. And transport of structure, well, it's rather the most natural thing given a bijection sigma from U to V. You can define the transport of structure as follows: summation I in I Fi of sigma. Now this will be applied to some element S comma I. We'll take the second model here. So this means that S belongs to FIU. Then this will be Fi sigma S comma I for every S belongs to FIU. And it's not difficult to check that this is actually a species of structure. Now, what happens with the generating functions? Firstly, note that we can assume without loss of generality I is countable, because for every for every set of cardinality n, Fi of every set U of cardinality n, whether FIU is trivial or non-trivial depends only on n. It doesn't depend on the set U. And so for each integer there are only finitely many cardinality elements I in I for which Fin is non-empty, and so totally there are only countably many I in I such that Fi is not the zero species. So for all but countably many I in I, Fi has to be the zero species. So we can just assume that I is countable, or in fact you can think of I as, if it's infinite, then you can think of I as the set of non-negative integers. And now what we would like to say is that if f is summation I in I fi for some summable family, fi I in I of species, then zf of x1 x2 is equal to summation I in I z fi x1 x2. Now this on the right hand side is potentially an infinite sum, and so we should also recall what we mean to say when such an infinite sum converges. I explained this very carefully when you just had a function of one variable, and there we had said, recall, summation n greater than or equal to 0 f and x converges if and only if limit as n tends to infinity f and x is equal to 0. This is for formal power series. Don't go do this in your calculus class. What this means is that so there's no topology on the field of coefficients here, and all we are saying is that that the coefficients, so for every, so suppose we have f of x equals summation n greater than or equal to 0 a n x to the n, let's maybe a n, let's call this m, then this condition that limit n tends to infinity f n x 0 is 0 is the same as saying that for every m greater than 0, there exists capital N greater than 0, such that for all n greater than n, a m n equals 0. Well, I can just write it like this, I guess. A m n equal to 0. What this means is that if you look at any particular coefficient of these series, then once n is large enough, that particular coefficient will always vanish. And you can extend this notion of convergence to a formal power series in infinitely many polynomials, like we have in infinitely many variables, like we have here, by just saying that the same thing happens to the coefficient of any fixed monomial. And in that sense, this hypothesis here of summability will say that for any fixed monomial, you can find for all but finitely many I in I, the coefficient of that monomial in the cycle index generating series for fi will vanish. And so in that sense, this series is actually convergent. This infinite series is a convergent series, and that sum is equal to ZF. I'll let you explore this a bit more in the practice problems, but I'll leave it at that here. And of course, obvious corollaries here are that you can also do the same, now you can talk about f of x. Well, that will be summation I in I fi of x, and f tilde of x is going to be summation I in I f tilde I of x. Let's look at a couple of examples. So the first example is what is called the canonical decomposition of a series, of a species. And it's the following: if F is a species of structures, define Fn to be the species given by Fn u is just equal to Fu if the cardinality of u is equal to n and it's empty otherwise. Then F is equal to summation n greater than or equal to 0 Fn. Okay, and of course you see right away that the generating series will also be sums. Here's an example of the example, taking F to be E. What we get is En u is just the singleton u if cardinality of u is n and it is empty otherwise. And the identity of generating series we get here is that E of x is E0x plus E1x plus and so on. Well, this is just x by x. The generating series of E0 of x, well, E0 has only one object of size size 0, so that's 1. E1 has only one, there's only one I shouldn't say object of size 1, I should say there's only one E0 structure on a set of size 0 and no E0 structures on larger sets. There's only one E1 structure on a set of size 1 and there are no E1 structures on any other sets. So here the generating series is just going to be x1 by 1 factorial, and then for E2 it will be x squared by 2 factorial and so on. So the individual terms in the generating series for E are the generating series for the ENs, and this is true in general for any F. The individual terms, the coefficients of the powers of x turn out to be the generating series. The monomials, I should say, turn out to be the generating series for the Fn's. And you can also try to see what the cycle index generating series decomposition here is. Well, it's not difficult. Let me just write it down. X1 plus X2. This we saw last time. And if you think about it a bit, what you'll get is this is the same as the way we calculated the series in some sense. This is equal to n, and then we have product xi raised to the power ki by I raised to ki factorial. So the summand corresponding for each value of n is the cycle index generating series for En. So this is Z En x1 x2, and this is of course Z E x1 x2. And if you want to look at the type generating series, well, E tilde x is just E tilde 0x plus E tilde 1x and so on. Well, E tilde x is just 1 over 1 minus x, which is 1 plus x squared plus x cubed. This is 1, this is x, and so on. Let me end with just a couple of more interesting examples, which we will come back to later. So let S K U be the set of all permutations maybe I should have two notations going for permutations. Let's stick to this. SU such that S has exactly k cycles. So we know that if U is a cardinal is a set of cardinality n, then this is given by the unsigned Stirling number of the first kind. So so what we have is yeah, and let's look at also par Ku to be S belongs to par U, where S has k blocks. Then what we get is S is equal to summation k goes from 0 to infinity SKU, and par is equal to summation k goes from 0 to infinity par ku. Okay, and recall we kind of know what these generating series are. SKU, its generating series is summation n greater than or equal to 0, unsigned Stirling number of the first kind Snk by n factorial x to the power n. X to the power n, yeah, that's right. Sorry, skx, and par kx is sum n greater than or equal to 0 s n k Stirling number of the second kind x to the n. Last example, if f is any species, n any non-negative integer, then nf, well, this is f plus f plus f n times, a sum of n copies of f. Then just from the definitions, what you see is that nfu is fu cross n. You can think of it as n disjoint copies of fu, but as I explained earlier, you can also think of the ith copy as fu cross singleton I, and so when you take the union, you get fu cross n. And z of nf, it's just multiplication by n at the level of generating series. Okay, so with this, I think we have a pretty decent idea of what sums of species are. In the next lecture, we will see how to multiply species.